If your vector search is fast but wrong, or right but slow, here is a local demo that shows which HNSW knobs move recall and speed. You have a library of embeddings and a deadline. You want relevant neighbors and responses that arrive quickly. By the end of this video, you will see a simple local demo that trades off recall and latency. And you will know which parameters to tune first to meet your target. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. HNSW is a practical index for nearest neighbor search. It shines when you need subsecond lookups over many vectors. People reach for it because it keeps accuracy high while using graph shortcuts to avoid scanning everything. Success looks like finding the same top results as brute force, but in a fraction of the time. At a high level, recall measures how many of the true top neighbors your approximate search returns. Latency is how long a query takes. We will build a tiny corpus, compute a ground truth, then try coarse buckets and a simple EF-style scan to see how recall and scan cost move together. We will build a small local demo so you can reproduce the trade-offs. The code stays small and explicit, so the knobs and numbers are easy to follow. Now we start with a baseline that finds exact nearest neighbors, so we have something to aim for. This snippet builds a tiny vector set and computes an exact nearest neighbor baseline. It creates a compact corpus of vectors and a handful of queries, then computes true nearest neighbors by exhaustively comparing each query to every vector. The core idea is brute force nearest neighbor, which means compute all pairwise distances and pick the smallest ones. Key lines create the vectors, pick queries, and run the exhaustive distance loop to produce the baseline hits. That baseline gives us the ground truth recall target. Later, we will compare approximate searches back to these exact hits to measure how many true neighbors we recover. Now, we coarse the space into buckets by centroids, so the search can prune large regions. This snippet partitions points into M coarse buckets using centroid assignment. The snippet first chooses M centroids, and then assigns each corpus vector to the nearest centroid, producing coarse buckets of candidates. The core idea is vector quantization, which groups nearby vectors so a query only examines a subset of the corpus. Important lines pick centroids, compute distances from each vector to each centroid, and record bucket membership. The parameter M controls coarseness. A small m makes large buckets with many vectors, which keeps recall high but increases work per bucket. A larger m makes many small buckets, which reduces per bucket scans, but risks missing true neighbors if you look at too few buckets. Next, we try an F-style scan that visits the closest buckets in order. This snippet performs approximate search by scanning F nearest buckets to the query. The idea is simple. For each query, you compute distance to all centroids, sort those centroids by proximity, and then gather candidates from the top EF buckets to score precisely. Key lines compute centroid distances for the query. Choose the EF nearest centroids, then merge all vectors from those buckets and compute exact distances on that smaller candidate set. The EF parameter controls how many buckets we inspect. A small f means less work and lower latency, but lower recall. Increasing f fetches more buckets, raises recall, and increases the candidate set and the time spent scoring. Now we measure how candidate count and time change when we change EF. This snippet compares candidate scan cost for small versus large EF settings. It runs the approximate search for different EF values and records how many candidates each query ends up scoring, which is a proxy for work and latency. The core flow gathers candidate counts and timing for each EF, then compares them side by side. Important parts show that doubling EF tends to increase candidate load in a roughly proportional way, and that query time tracks candidate count. The comparison makes the trade-off concrete. Small EF gives small candidate sets and fast queries, but misses some true hits, while large EF recovers more hits at the cost of more scoring work. Finally, we pick the smallest F that still hits the exact baseline. This snippet selects the smallest F that reaches the exact baseline hit. It evaluates recall across a sweep of EF values and picks the minimal EF that meets the baseline recall threshold for our queries. The main idea is empirical tuning. Run EF candidates from small to larger values and stop when recall matches the brute force baseline for your acceptance criteria. The snippet highlights how quickly recall often rises with EF and where diminishing returns begin. This gives a practical rule of thumb. Choose the smallest EF that achieves your target recall to minimize latency without sacrificing correctness. Mapping this toy demo to a production flow is straightforward. Replace the tiny corpus with your real embeddings and use an HNSW index implementation for graph traversal. Keep the same tuning loop. Measure baseline with a holdout, sweep EF or M, and pick the cheapest setting that meets recall goals. Also, log candidate counts and query times as you scale so the trend remains predictable. Recap in 3 crisp points. What it is: a small demo showing how coarse buckets and EF control the search recall and latency. When to use it: when you need to trade a small loss in recall for much faster query time. One caveat: tuning is data dependent, so results on this tiny set are a guide, not a universal answer. Next step: pick either M or F and run a quick sweep on your real holdout set to find the minimal F that meets your recall target while keeping candidate counts low. If short, practical AI engineering helps, subscribe and watch the AI engineering videos.